I'll try and make this full screen. All right, not bad. Okay, so today we're going to do this lecture on the iPad. I don't know how this is going to go. The space is a little cramped here, and hopefully my computer doesn't die, although it looks like it could die. We'll just see what happens here. Okay, so, oops, this thing already not working. Oh, okay. All right, so today we're going to be talking about two main algorithms that are related to each other. So we're going to talk about gradient descent, and we will talk about backpropagation. And in doing so, we'll also touch on a couple of different important concepts, including the cross-entropy loss, which is what we're going to be using for, okay, I'll try not to write past there, for language modeling. And when we talk about backpropagation, we will also talk about it within the context of our concatenation and then feed-forward language model. And if we have time at the end, we will also talk about it in context of a recurrent neural network. So in both of these examples for this class, we'll be looking at just single neuron examples. So we won't be looking at matrix vector gradient derivations here, but if you're curious about those, there's a link in the lecture schedule to a previous video where we talked about these things. Okay, so I'm also noticing this battery percentage going down here. So I guess we have a finite cap on whatever time we have for this lecture. I should get that fixed at some point. There's so many cords here. All right, anyway. So let's just do a quick review of the concatenation feed-forward neural language model that we talked about last class, specifically the forward propagation steps. Oh, I should mention I can't see the YouTube chat right now, so I'll try and periodically look at those. So remember here in our running example, we were given the prefix students opened there, and we asked the model to predict the target word books, right? So our basic setup was we're going to have a vector for students, a vector for opened, and remember these vectors we call word embeddings. They're part of the parameters of the model. Students opened there, and oh, I put this down too far. Down here. So then we concatenated all of these things together, and we got this H vector, which we also applied a linear layer to do this dimensionality reduction. So here we did the concat and feed forward using a weight matrix W sub 1. We'll go over the equation in a bit. And then here we had softmax layer using matrix W sub 2, and eventually we obtained some sort of probability distribution over all the words in our vocabulary, and hopefully the one with the highest probability is something like books or laptops, right? So the parameters in this model, are what exactly? What are the parameters? Oh, I should put some terminology here. So these word embeddings are C sub i's. So what are all the different parameters in this model? And W1 and W2, right? So these are all the parameters in my model. All of these other things, namely H, and we can call this O, the output probability distribution, are just products of the parameters of this model. They're intermediate variables. They're not actually learned parameters. Okay, so let's look at the equations for this model. We have H equals F, where F is some nonlinearity. We take our weight matrix W sub 1, and the vector that we're multiplying with is this concatenation of all of the word embeddings in the input, right? So this here, the notation for concatenation. And then finally, we had just one other equation, which gives us our output probability distribution over the next word, right? So one thing that we did not talk about last time is how actually we train this model, right? So what does that question even mean? Oh, I keep turning this thing off. Okay, how do we train this model? So what do we mean by train? It means, well, we have a large set of training data, right? We've already talked about how in language modeling, we get data for free because we can take any piece of text and turn it into a predict the next word problem, right? So this question more specifically means, how do we adjust our model parameters? And note that we have all these parameters up here. So we're going to refer to the set of all of the parameters, which is called the parameter vector, as a theta. So that includes every single one of our model's parameters that we're interested in learning. So how do we adjust our model parameters theta to make better predictions of the next word? And these predictions we're talking about making on the training set, right? So initially, our model knows nothing about language. It doesn't have any idea of what the next word should be. But the next time it sees students open there, perhaps you would expect it to have a better prediction of, that books and laptops should have high probability. And then the next time it should be even better at doing this. So how do we actually go through this process and adjust our model parameters, this theta, to make the predictions better? So we're going to do this using a combination of two algorithms. We'll look first at gradient descent. And for any of you with machine learning background, this is going to be a review. But for others, this might be your first time seeing it. So we'll just go over it at a kind of high level. So there's essentially three steps in applying this algorithm of gradient descent. The first thing you need to do before anything else is define what's called a loss function. And we're going to call this L. L is a function of theta, our model parameters. And the role of our loss function is to tell us how bad the model is currently doing at predicting the next word. So there's some properties of this loss function that we would like to have. Ideally, it would be, mostly differentiable and smooth. Basically, we want like the local derivatives to be meaningful in searching for a minimum of this function. So our goal is to minimize this function, right? We want to get to a point where the model is not making that many errors as to what the next word is. Okay, so some properties, ideally smooth, differentiable, although, it doesn't have to be completely differentiable, just maybe mostly so. There's a lot of work on this. And the loss function that we will be using in language modeling world is called the cross-entropy loss. So this is not only useful for language modeling, but useful for any sort of classification problem. So language modeling is a classification problem, right? You're given some input, you're asked to predict something that comes out of a set of possible labels. Here, our labels are just the words in the vocabulary. So it's a large output space classification problem. Okay, so we're going to talk about the cross-entropy loss later on in the lecture, but first we're going to go over all of these different steps in gradient descent, and then go through how to compute the gradient for a very simple function. Then we'll talk about the cross-entropy loss. All right, so given some choice of loss function, like the cross-entropy loss or the square loss, there's many other different types of loss functions you could use. The next step is to compute the gradient of L with respect to theta, the model parameters. So what is the gradient? The gradient formally gives us the direction of steepest ascent of the loss function. But let's look more intuitively at what this means. So first of all, the gradient is the same dimensionality as the parameter vector. So if I had these things, C sub 1, C sub 2, C sub 3, W sub 1, W sub 2, I have all these different numbers in all of these 5 parameters, right? So you can imagine I just roll up all of these numbers into a single vector, which is now my theta. It contains all of my parameters. The gradient is going to be the same dimensionality as that theta. So for every parameter I have, I'm going to have a corresponding derivative of the loss function with respect to that parameter. The gradient is the set of all of these partial derivatives with respect to all of the different parameters. So this will be a little more clear when we go through an example, but it's the same dimensionality as theta, the parameter vector. And for each parameter, so let's just say parameter j in theta. So there are many different parameters as part of your model. For a single individual number in your parameter vector, or dimension of your parameter vector, it tells you, it being the gradient, how much the loss function L would increase if you increase j by a very small amount. Okay, so this is very useful, right? Because we want to change our parameter vector to make L as small as possible. So what we want to do is compute the gradient and then adjust our parameters in the direction of the negative gradient. So our function is getting smaller and smaller and smaller. That's the general idea. So that's actually step 3 here, given the gradient. And we're going to use this terminology for all of our partial derivatives. So here this dl over d theta represents the gradient of the loss function L with respect to the parameters theta. It's a partial derivative, right? When you look at all of the different components of theta, you can compute dl, dc1, dl, dc2, dl, dw1. All of these things together form the gradient. Anyway, our goal is to take a step in the direction of the negative gradient, right? Because the gradient gives us the direction of steepest ascent, again, and we want to be going down. So we go the opposite direction. What should I highlight here? Maybe this. Which thus minimizes L. So basically what you do is you have your theta, which let's call theta old is your old set of parameters. Now you want to make an adjustment to theta so that your predictions get better and your loss gets smaller. So theta new is going to equal theta old minus some eta, which we call the learning rate, times the gradient of this. So this is the gradient here, and this thing is called the learning rate, which controls the step size. So you don't want to make a huge step in the direction of this gradient. You want to make, but you also don't want to make a very small step because you want your convergence to be reasonably fast. So it's a hyperparameter. Again, we talked about hyperparameters in the last class. It's something that you probably try a bunch of values and see which one converges the quickest or which one reaches the lowest loss or so on. And there's many ways that people have to learn these learning rates per parameter. They can adjust them or so on, but intuitively it's just controlling the step size, and you need to find a balance. So let's take a look at a example, and maybe it'll be a little more clear. So let's just assume I have one parameter in my network, and I have a loss function. So I can plot this in 2 dimensions. So here is my loss function on the y-axis, and then the value of my parameter on the x-axis. So let's say the loss function looks something like this. Obviously, my goal is to get to the bottom of this, which is the minimal loss, right? So let's say that before I see any data at all, I, of course, have to give some initial value of my parameter, right? I don't know what it is. I'm completely uninformed as to the data. So it could be anywhere on this curve. Let's say we start over here. So we have a pretty high loss, but this is our random initialization. So we'll call this theta sub 0. This is where we start. So now we're going to compute the gradient of the loss function with respect to theta sub 0. And we might find some direction like this. The negative direction is what I'm showing here. And so we're going to take a step in that direction, and we might get here. So you can see that if I keep recomputing this gradient and keep taking steps, it'll take me down to the minimum here. But what happens if my learning rate is too high? So let's say I compute this derivative again. And it's telling me to go somewhere over here. And then my learning rate is really high. So what could happen is I overshoot where I intended to go and end up like somewhere over here, which would be bad, right? Because I've missed this local minimum. My learning rate was too high, so I couldn't take full advantage of the direction that this gradient was giving me. So then if I compute it again, and now maybe here I'm like, okay, that was an unreasonable learning rate. Eventually, ideally, I will get down to the minimum of this function, and I have learned my parameter such that it gives me the lowest loss on my training set. And now I hope that this model here will generalize to data outside of the training set. All right, so what are some important things to know here? There are 2 important hyperparameters that we'll talk about at this juncture. One, of course, is the learning rate. So we've already talked about why that's important, and we will see as this class goes on many different ways of choosing that and better optimizers than just the simple gradient descent that I'm talking about. Another thing that's important and may not make sense now, but we'll talk about at length later on in the semester, is called the batch size. So in general, when you have a training data set, there are a bunch of ways you can estimate the gradient, right? So I could, for example, let's say I have 100 examples in my language modeling data set, in the training data set. I could pass each one of these 100 examples through the network, and only after I see the entire training data set do I compute the loss and compute the gradient and then take a step. So this is called full batch gradient descent. I look at the entire training data set before making a step. Another way I could go is after every single training example, I could compute the loss, compute the gradient, and then take a step. So here, I get way more steps than in the previous method, but my estimate of the gradient is not as reliable, so I could have noise. So the in-between is called mini-batch gradient descent, where you don't look at the full training data set, but you don't look at just one. You look at some number k of examples. You compute the loss over those examples, you compute the gradient, and then you take a step, and you're trying to balance like the reliability of the gradient, the variance, with the number of updates that you can actually make. So this ends up being a hugely important hyperparameter for many of the models that we'll discuss later on in the semester. So I guess we can just summarize it by how many training examples do you use to estimate the gradient before taking a step. All right, so I'm at 71%. I think I could actually make it through this lecture. Let's see if there's any YouTube questions. Okay, at the first layer, do we concat and then multiply with W1 as in the equation, or multiply with the weights and then concat? So we do the former. We first do the concatenation, then do the matrix vector product. In gradient descent, we generally find the local minimum rather than the global minimum, right? So when we're working with these highly non-convex loss surfaces, as we see in these nonlinear neural networks, we are not guaranteed to find the global minimum, as we showed on this simple example, right? Our loss function will be very complicated, and generally we will find a local minimum, which may not be the global minimum, but there's been a lot of work studying these loss surfaces and seeing basically that even if you find a local minimum, it's usually still a pretty good solution in general. And these gradient descent style methods do work even for these non-convex loss functions. So yes, you're right in the setup that we're looking at here. Okay, so questions from the class? No. I mean, this is just a one-dimensional plot here. The loss, generally, our parameter vectors could be millions or billions of dimensions. In each one of those, we're computing a partial derivative of the loss with respect to that. So it's very hard to visualize what's happening in this, but it's not like this where there's one clear global minimum. Yes?
Okay, so when we define batch, would it be better to have examples of the same classes like clubbed together in one new batch, or should the batch be a larger representative of the entire training data?
Oh, right, I forgot to say the questions. I'll say your question. Yeah, the question is, when you're doing batch gradient descent or mini batch gradient descent, how do you choose a representation in the batch with respect to the labels? Like, do you choose all the same label in a batch, or do you choose randomly, or what do you do? In general, in something like language modeling or most tasks, we do this at random. So we shuffle the data set. Although with language modeling, it's a little more complicated because you are predicting the next word, and your input is generally not just a single prefix and the next word, but it's actually a long sequence which you can then splice into multiple next word predictions just by adjusting which word in the sequence you're currently predicting. So a batch in language modeling is generally randomized at the sequence level, but within a sequence you're going to be making all the predictions for the words in that sequence. So that is pretty complicated, but it'll be more clear when we talk about batch training in later lectures. Yes?
You mentioned that people have strategies to optimize the learning rate. Are there similar strategies to optimize the batch size?
So the question is, are there strategies to optimize the batch size, or are there any tricks that people use? I don't. So lately, it seems like the trend is to just use a larger and larger batch size, because in general, if you're dealing with language models, you have way more data than you can ever basically estimate with, like, take a full pass through the training data set, might even be impossible. Like, I think in GPT-3, they didn't even take one pass through their training data set. But in these cases, it is always advantageous, it seems, to train with as big of a batch as possible. But you have to balance that with being feasible, right? Because if you don't get that many updates, then it's going to take you a lot longer, a lot more compute to be able to get your model to converge. So yeah, I think based on my students' research, it seems like bigger batches are almost always better, but you need to have the compute to do that. It probably depends on the problem too. I'm just speaking for some things like language modeling and related problems. All right, any other questions? While my battery slowly bleeds out. Okay. Let's move on then to backprop. So we're going to get to the loss function used in language modeling a bit later, but I just wanted to kind of tie up this thread and show you how to compute these gradients, because that's what's missing, right? I haven't actually told you how to get this DL d theta. All right, so hopefully this thing works. Let's look at a simple example. And in all of the examples that I'll show today, we're going to be looking at single scalar neurons. So there's no vectors and no matrices. Everything here is a scalar, the intermediate variables, the parameters, and so on. When you're actually implementing these models, nothing will be a scalar. Everything will be a vector, and you're going to be dealing with matrices, and if you're doing batches, you'll be dealing with tensors. We'll have a more practical implementation-focused class where you can kind of visualize those things better. But for now, we're just trying to learn the basic intuition behind the backprop algorithm. So let's take this incredibly simple neural network. We have an input, x. Again, this is just a single number. We have a hidden layer, h. So we're going to have a parameter, w sub 1. Again, this is a scalar, not a matrix. That's used for transforming our input into h. And then we're going to have an output, o, and we're going to use another scalar, w sub 2. This is a parameter to transform h into o. So our inputs are x, y pairs. These are our training data set. So x is the model input. Y is the target. So this is our training data. We already know what target we want. So for example, this could be something like 5 and 4.3 as our intended output. So we want to train our model such that if we give it 5, our output is going to be 4.3, our O. Of course, this is a completely useless network, but this algorithm forms the building block of many more complicated and useful networks. All right, so let's say our network is defined just as a feed-forward network would. Our h is tan h of w1 times x. Note that this is not a matrix vector product. This is just a multiplication of two numbers. And our O is tan h of w2h. So very, very basic network. Okay, so what's our first step of our algorithm? First, we need to define some sort of loss function, right? So here, we'll use probably the simplest loss function, which is the square loss. So the square loss is defined as follows. And this is square loss. You might also see it called the L2 loss. It's generally good for regression problems, not classification problems. So in a regression problem, you're basically trying to predict a continuous valued output like 4.3, as opposed to a discrete class like in a classification problem where I'm trying to predict books. But this loss function is super simple, so we'll start with it. So here again, y is our target, which we get from the, so we get our y from the input. We already know what y should be, and we're trying to make this network predict y. So you can see that our loss function here our loss function here is basically telling us that if the difference between y and o is small, the loss will be small. If the difference is large, it'll be large intuitive. So O here is the model's prediction. All right, so we have this loss function, and now we're going to compute the gradient. So since our equations are pretty simple, this will also be simple. And remember, the gradient is dl d theta, and here theta consists of only, well, what are the parameters in this model? Yeah, W1 and W2, right? X is part of our input. We're not training X. H is an intermediate variable. O is an intermediate variable. So when we say we're computing the gradient, we are computing exactly two partial derivatives here. The partial derivative of the loss with respect to W1 and dl dw sub 2, right? There's only two parameters in this network. Okay, so at this point, it's important to remember the chain rule of calculus. So I'll write important chain rule calculus. We've already looked at the chain rule of probability. Now we're going to look at the chain rule of calculus because it's kind of fundamental to backprop is nothing but applying the chain rule of calculus and then doing some caching of the derivatives, as we'll see later. So if you want to differentiate a function g, which is itself a function of f of x, another function, this is just first you differentiate g of x with respect to f of x, then you differentiate f with respect to x, right? So chain rule of calculus. And here, since we're taking these derivatives, this is going to be very useful. So let's actually go through. So when we're doing backprop, it's important to start with the parameter that's used as close to the output as possible, and then go down deeper in the network from there. This will make sense as we write out these equations. But let's start with our loss function, y minus o squared. And now O equals tan h of W2H, right, as per our model equation up here. And also, one thing that's helpful when we're differentiating these things is to make some even more intermediate variables so you can easily compute these derivatives. Here, we're going to make two intermediate variables just to make our lives a little, at least make the explanation more coherent. So let's make intermediate variables A, which is going to be W2H, and B is going to be whatever's in this one, W1X. So now we can rewrite this equation as tan h of A. Now A equals W2H, H equals tan h of W1X, which is actually what we called B. So I'm going to erase this and put B, and then B equals W1X. So now we have just this sequence of very, very simple functions. And we can go ahead and apply the chain rule to compute the two partial derivatives of interest here. So let's start with dl dw sub 2, because this one comes closest to our computation of the loss function. So if you look at where w sub 2 is used in this network, you can see that w sub 2 is used in the computation of O in the loss function, right? Because this O is a function of this intermediate variable A, which includes this w sub 2, right? So if we trace our way back and apply the chain rule to compute this partial derivative, we're going to compute dl do times do dA times dA dw sub 2. So just applying the chain rule of calculus, this is how we compute this derivative. So one thing that is useful to know at this point is that the derivative of tan hx, tan h is just our nonlinearity in this particular example network. It could be any nonlinear function, but tan h has a nice derivative. It's 1 minus tan h squared of x. And this means you don't actually have to compute anything. If you compute the tan h, you can just square it and then subtract it from 1 to get the derivative. So if we look at the applying the chain rule to compute this partial derivative right here, first we'll start with this term, dl do. So what is this? We know that O is used in this computation of L. So if you use the chain rule here, what would you get as this derivative? Someone just raise their hand. Okay. Well, if you look at this, right, there's a -1 multiplied to the O, and then it's in the squared term, so you just use basic differentiation rules, and you'll get this, right? This is the partial derivative of L with respect to O. Now, this just directly follows from the definition I've given you up here. O equals tan h of A, so dO dA, we can just use this here and get 1 minus O squared. And then dA dW2, all right, this should be pretty simple. H, right? So it's just this. And this thing altogether is our partial derivative when we multiply these three terms, right? So now what we're going to do is do the same thing, except look at dl dw sub 1. So here, if we trace our way back like we did before, we're just going to remove this last arrow here. So where is w sub 1 used in this network, right? It is eventually going to make up the computation of O through A. And then here, we're going to look at A through H. Whoops, I wanted to use this other color. H, right? So instead of dl dw sub 2, we just stopped here because w sub 2 was just used in this computation. Now we have to differentiate through H as well. H is a function of B, and then finally we get to w sub 1. So when we write out all these terms here, we get dl do times do dA times dA dH, dH dB times dB dw sub 1. Okay, we're not actually going to compute out all of these things, but the important thing to note is that these two derivatives actually share some terms, right? In particular, they share this term and this term. These are equivalent in both of these partial derivatives, right? So when I get to computing dl dw1, it would be foolish of me to recompute these terms here, right? Because I already computed them when I was computing dl dw sub 2. So it would make a lot of sense when I'm computing dl dw sub 2 for me to cache these values or the product of these values. And then that way I don't have to start from the very top again when I'm computing dl dw sub 1, right? Instead, I can just compute these terms here new. And if I had something even further down in this network, I could cache more things of this and use them for the derivatives further down. So with that intuition, that's literally all backpropagation is. Chain rule of calculus plus caching previously computed derivatives. Okay, so in 2022, you're not going, if you want to implement a language model, you're not going to have to write these partial derivatives for every single parameter in your network. That would be a very annoying task. There are libraries that automatically do this for you. So in particular, something like PyTorch or JAX or TensorFlow, you would just have to specify these forward equations up here and specify your loss function. And you feed some training data through your network. The libraries will automatically calculate all of these derivatives, and you can update your model parameters without actually going through any of this math. But of course, it's always good to know what's actually going on under the hood, and it's all just calculus and some intelligent caching. When we look at matrix vector and differentiating through those things, there's a little bit of tricks that are used to make those computations more efficient. You can check out the video that's linked on the schedule if you want to learn more about that, but there's nothing too fancy going on here. Of course, some of the functions that you could be differentiating could be very complicated, but in libraries like PyTorch, they basically break everything down into these primitives for which they already know the derivatives, and then we're not going to talk about how to actually implement one of these libraries, but it's definitely not required to implement any of these models. All right, so let me take some questions. Can the learning rate change dynamically as the model gets trained? Yes, and it often does using more advanced optimizers. So the most popular ones nowadays are things like Atom or AdaGrad or stuff like that. The rules that we've looked at here are just basic gradient descent, so the learning rate doesn't change. But yeah, in most state-of-the-art models, the learning rate is changing dynamically, not only as training goes on, but also per parameter. You might have a different learning rate. How do we ensure that the loss will converge to global minima instead of local minima? We can't ensure this. We don't know if we have a really complex loss surface, but in practice it seems to even these local minima that we seem to converge to do pretty well. Numerically, what do we backpropagate when we work in batches? The mean of the loss per batch, and this only at the end of each batch? That's a good question. So yes, usually we're backpropagating. We compute the loss per example, take the mean, and use that as our loss function, compute the gradient of that. So yes, at the end of each batch, this is when this is computed. All right, any questions from the class? How are we doing on time? Okay, so right, I forgot the third step here of our gradient descent, which was just to update our parameters. So this is very straightforward. Now that we actually have these two derivatives, we're going to compute, say, W2 new equals W2 old minus the learning rate times the derivative that we just computed, and the same thing with W1 Okay, so with this, we've just made this network be better at next time when it sees the input 5, hopefully the output is closer to 4.3. That's basically what we wanted to do. All right, so at this point, I wanted to shift our focus to the loss function and talk about the cross-entropy loss, which is useful for language modeling and general text classification. After we talk about this, if there's time, we'll look at recurrent neural networks in this scalar setting and doing backprop through those. So what loss function is used in language modeling? It's the cross-entropy loss. And generally useful for any classification task. So here, if you recall our language modeling setting, we had students opened there. This was our input. We vectorized this using some neural network, which gives us a vector. And then, using that vector, we tried to predict books. So books is our target. And we have a total of V labels, where V is the size of the vocabulary. This is a classification problem with V labels, and books is just one of those V labels that we would like to predict given this prefix. Okay, so recall in language modeling, our goal is to maximize this conditional probability, the probability of books given students opened there. So if students opened there occurred in our data, we want to maximize this probability, right? That should be our goal. We know from our discussion of loss functions up till now that we like to minimize our loss functions and go in the direction of the negative gradient. So what we do for training these models is minimize the negative log probability of books. So our loss function here is negative log P of books given students open there. And we talked about, all the benefits of working with logs in the last class. But there's also connection to information theory, which is apparent in the name of this loss function, the cross-entropy loss. So this is the loss function that we use in language modeling. It is the cross-entropy loss. And why is it called the cross-entropy loss, right? You might be wondering. So the cross-entropy in general is a measure of essentially similarity between two probability distributions. And in this case, we do have two probability distributions. So the first one is kind of obvious, right? We have the model's predicted distribution, which we'll call Q. And so if I take my network from before, all right, let's see if this works. So I had this network, right? And at the end of this, I got some distribution, like, there's some probability on stamps, some probability on lamps, and some probability on books. So let's just use some color to make this. So this is our distribution Q here. And this is what the model is predicting at this particular setting of its parameters theta. So it's obviously not perfect. It thinks that lamps are more probable here than books. And this is what we want to change to make the probability of books higher. So in our data, we observe this prefix, like a lot of words, and then students opened there. And in the data, there is only one word that follows this prefix that we've observed, right, which is books. So our data distribution is going to have 100% of the probability on books and 0% on all of the other words in the vocabulary. So this forms, this forms our target distribution, which we're going to call P. So if, given this specific prefix, our model is putting almost all of its probability on books, then our model would minimize this loss function, right? Because our ground truth distribution is saying that 100% of the probability mass should be on books given this context. All right, so basically here, P of books given students open there is 1.0. All right. So then the definition of cross-entropy between two different discrete distributions between P and Q is, so we're going to sum over all of the different words in our vocabulary, or all of the different classes, and it's P or times the log of Q, the probability of W under the model. So just to use these colors again, have this. And now if you look at this, you can relate it back to what we set up here our loss function is, which is negative log P of books given students open there. If you look at this, P of W here, this is our data distribution. It's 1 for books. So, sorry, it's 1 when W equals books, and 0 for every other W. So when W is books, this is 1, and every other time this is just 0. So this simplifies then to the negative log probability of the model's estimate of students, or books given students open there, because all the other terms here, this P of W is just 0, so they don't appear in this. So again, the cross-entropy function for language modeling when we're using the maximum likelihood estimate to train our model is just the negative log probability of the correct word. Okay, so we're going to see this loss function over and over again. It's useful for language modeling and thus useful for everything in natural language processing. One thing you might wonder is, well, why is our data distribution putting 100% of the probability on books if there are other things in the vocabulary that might make sense given this context? So here, because we are trying to maximize the likelihood of seeing our data, this is the probability distribution that does that, right? Given this prefix that we observed in the data, we saw just this one word that follows. So you could imagine we have the same exact prefix sequence multiple times in our data set, and after each one, we see a different word. So maybe one time we see books, one time we see laptops. So what happens here? If in both cases the model is going to be presented with, it has to compute a probability distribution. In one case, the target is 100% books. Another case, the target is 100% laptops. To get the lowest possible loss, the model here is going to have to put equal probability on books and laptops. So this is one reason why this still works in this circumstance. All right, so any questions about the cross-entropy loss? No one on YouTube? No one up here? Okay, so we have 20 minutes left. I think that should be enough time to go through recurrent neural networks. So in the next lecture, we will be talking about attention mechanisms in recurrent neural networks. In this lecture, you'll get a quick idea of what they are. We also talked about them towards the end of the last lecture. But here we'll go into some of the equations and the backprop specifically. Again, just with a single scalar neuron, no matrices or vectors. So remember again why we were even talking about recurrent neural networks, right? They had many advantages compared to those fixed window concatenation-based language models. In particular, they could theoretically handle arbitrarily long prefixes, right? Because you're just applying the same equation left to right. So there's no limitation on, like the model's parameters are not bounded by the length of the input. They also shared their parameters at every time step of the network. So the model is essentially using the same parameters to process a word regardless of which position it appears in. So the model size is also reduced and so on. So this used to be the state-of-the-art class of models before about 2017 when the transformer came along. And in the next lecture, we'll be talking about attention mechanisms, which are integrated first into recurrent neural networks and then kind of lifted out of recurrent neural networks and made their own thing with the transformer architecture. But let's not get ahead of ourselves. So in the recurrent neural network, remember we start with this initial hidden state, h sub 0. Then we have two different inputs at every time step. We have the previous hidden state, and we have the input word at the current hidden state. So here, we have to compute h1. First, we use some parameter w sub h in order to transform the previous hidden state into the current hidden state space. And then we do, we have some word embedding here. We have a separate parameter that does this projection. So our graph here looks something like this. When we're going from h1 to h2, we use the same parameter that we used at the previous time step, w sub h. When we incorporate a new input or new word here, we use the same parameter w sub e that we used at all the previous time steps to do this. Here, let's say we have another parameter that gets us our output. So you can conceptually think of this as students opened and then this as some probability distribution. Here, we're not going to talk about backpropping through the cross-entropy loss. Instead, we're just going to use our standard square loss because it's easy for demonstration purposes. All right, so our usual exercise, what are the parameters of this recurrent neural network that I've drawn up here? Okay, well, there's no W1. There's a WH and a WE. There's a WO. And in this case, unlike in the previous example, we are also learning the word embeddings, right? The word embeddings are part of our parameters. Here, they might just be single numbers, but they're still part of the model. So we have these 5 parameters here. So if you notice, the difference between this case and the feed-forward concat case, the feed-forward network that we looked at in the previous example, here, if I want to compute the derivative of our loss with respect to w sub e, there's multiple occurrences of w sub e in this network, right? Similar with w sub h. So the other things are quite straightforward, but these 2 parameters require a slight modification of our algorithm. But let's just define some equations first. So our loss function is the same as before. We have some target y. We want to get close to that target. O here is going to be WO H2, and then H2 is going to be tan H of WE C2 plus WH H1. So we're going to say this is some intermediate variable A here, whatever is inside of the tan H. And then H1 is WEC1 plus WH H0. And of course, we can say this is some other intermediate variable B. And now we have defined our recurrent neural network here, and we want to compute some partial derivatives. So the easiest thing is to start at the thing closest to the output, which is W sub 0. It's only used once in this network. Should be pretty trivial to compute this partial derivative. So we want to compute dl dw sub 0. Sorry, w sub o. This is dl do times do dw sub 0, which we know this first term is just this, and the second term, do w sub 0, is just h2 from this equation, right? So this is all straightforward. It just follows from the chain rule. Let's look at dl dc2. So c2 is only used once in this network, so it should also be fairly straightforward to compute. But it's a good exercise, right? We have to navigate now from O to H sub 2, then down to C2. So this looks like dO times dO dH2 times dH2 dA, our intermediate variable, and then dA dC2. So we could write all of this out. Again, if you look at it, these two things share one term, the dl do, which we might want to cache. This do dH2 is w sub 0 now, not h2. And then dH2 dA, that's just applying our tan h formula. So we get 1 minus h2 squared. And then finally we get dC2, which is just WE. So, okay, nothing fancy here. We could do the same thing for C1 and get a much longer product of things. But what is more interesting in this equation are dL dWE and dL dWH. These are trickier because they are shared. Sorry, shared is not the best word. Maybe they are used at multiple time steps in the network. So by time step, I mean in this recurrent neural network, we have time step 0, where we just have h sub 0, time step 1, h sub 1, time step 2, h sub 2, and then our output. So each time we compute our recurrent neural network update equation to get a new h sub n, we call this a time step. So what is interesting about WE and WH is that they are used at multiple time steps. So computing their derivative is not, I mean, it's still straightforward, but it's not as straightforward perhaps. The way you do this is using a variant of Backprop called Backprop through time, which is very simple. It basically means you unroll this recurrent neural network into a deep feed-forward neural network, and you sum the contributions of so all these different derivatives that you get at each time step, you sum it across all of the time steps. So let's be a little more clear. Allows us to compute these by summing contributions from different time steps. That's supposed to be time. Okay, so let's just do dL dWE just to explain what I mean by that. So if you look at WE, it's used here, and it's also used here. So let's just compute, let's assume it's not used at time step 1, and let's just compute the contribution to this gradient when it's used at time step 2. This should be pretty straightforward, right? It's just the same thing as dL dC2, except we changed the last product, the last term in the product. So it's dL do times do dH2 times H2 dA times dA dW sub E. So we have to go, this last term from this is replaced with dA dW sub E. Right? So if it were only used at one time step, this would be completely sufficient. But it's actually used back here as well. So the actual derivative here involves the sum with its use in the previous time step as well. So now we have to write out a lot of these things, dH2 dA. And now here, instead of differentiating with respect to W sub E, we're going to go deeper into the network, differentiate with respect to H sub 1. Now we're in the previous time step. We're going to differentiate with respect to the intermediate variable. And then finally, we get to here. So now you'll note again that these two terms have a lot of shared components, right? So like all these things are shared and could be cached. And in general, when you're computing these kinds of derivatives, you're going to accumulate them over multiple time steps. So I'm going to compute the derivative for W sub E when it's used at time step 2. And then when I've computed all my derivatives at time step 2, I'm going to take a step back and add the contribution from time step 1 of W sub E's derivative to what I computed at time step 2. And I can do this for as many time steps as I have in my input sequence. So, and this is the same thing I would do for W sub H as well. See, that one is also used at multiple time steps. So we, oh, what just happened? We can accumulate these dL dWE or dL dWH as we step back through time. So note that in a recurrent neural network, we always start backpropagating from the very last time step and then go iteratively until we get to the first one. So it's the reverse process of the forward propagation step. All right. So then I guess I will end before taking some questions with a quick nod to the what's known as the vanishing gradient problem. So this is an important weakness of recurrent neural networks. Basically what this is saying, and there's also a counter situation to this problem, which is called the exploding gradient problem. These gradient contributions from far away time steps go to 0. So if you note, all of the different components that we're summing together, they have many of the same terms in their computation, right? These two things share the first 3 terms. If you imagine I had another time step, might share the first 6 terms, and so on. So I'm multiplying more and more and more and more of these numbers together, right? And depending on certain properties of this number, this could make it such that if I have a lot of terms, each of these things that I'm summing gets smaller and smaller and smaller every time I step back in time. Or it could get bigger and bigger and bigger, right? And so this makes it hard practically to get any sort of learning signal from information way back in the past if the contribution to the gradient is so minimal. So there have been many variants of recurrent neural networks proposed to deal with this problem to some degree. So some of you might have heard of LSTMs or GRUs, which have some augmented memory capability that allow the model to kind of bypass, like it can write to some memory and then not update it for some time steps if it wants. and as such preserve some information over longer distances. And another thing that helps with the vanishing gradient problem is the attention mechanism, which we'll talk about in the next class. So this lets you directly skip. So maybe if you're at time step 10, and it would be really helpful to get information from time step 0, you can kind of skip all of the intervening time steps and focus your attention on the time step in the past that you want. It's kind of some intuition. It'll be more clear in the next class. All right, so I think that's mostly all I wanted to say. Let's see if there's any more questions. Are LSTMs and GRUs always better than RNNs, or could there be cases where RNNs are better? This is kind of an empirical question. So LSTMs at least have more parameters than RNNs. So if you have a very small data set, maybe you would be, and maybe your data set doesn't have any long-term dependencies or any very long distance dependencies, maybe an RNN would do fine. It's just an empirical problem. It depends. For any question like this one, the answer is it depends on the data set that you're training your model on, the size of your model, and all these hyperparameters that you've chosen. So there's no clear answer to, there are going to be situations where RNNs could be better, there could be situations where these other things are better. In general, LSTMs are better language models, at least, than RNNs. What is the benefit of using transformers? Well, we'll talk about that when we discuss transformers. All right, any questions from the class? Yes. Skip connections, yeah, you could easily. Actually, I had one exam problem a few semesters ago where I asked people to do backprop for an RNN with skip connections. So like your current time step would be dependent on the previous time step and the time step like 5 connections ago or something. So yeah, you could do things like this, but again, every time you add one of these connections, you add some new parameters, and the model has to learn how to use that information. It might not always make sense, right, to have such a connection. Other questions? All right, see you on Wednesday.